All right, let's just jump right in. Think about everything you can see. The stars, the planets, galaxies, even yourself. Now, what if I told you that all of that is just a tiny, tiny fraction of what's actually out there? Yeah, most of our universe is made of something we can't see at all, a kind of cosmic ghost that shapes everything. Today, we're going on the hunt for dark matter.
I mean, just look at this chart. This breakdown of the universe it's just staggering. Everything we know, all the ordinary, normal matter that makes up every single star and planet, that's only 5% of the cosmos. Just 5%. Then you've got this huge chunk, 27%. That's this mysterious dark matter. And the rest? That's an even weirder thing called dark energy. So think about it this way. For every 20 pounds of stuff in the universe, only 1 pound is the stuff we can actually see.
You know, NASA has a really great way of putting it. They call dark matter the invisible glue that holds the universe together. And that's such a perfect analogy, isn't it? It doesn't shine, it doesn't reflect light, but its gravity is so powerful that it acts like a cosmic glue, keeping entire galaxies from just flying apart. It's like the invisible scaffolding that the whole universe is built on.
So if we can't see it, how on earth do we even know it's there? Well, let's treat this whole thing like a cosmic investigation. We've arrived at the crime scene, and while we can't see the culprit, its fingerprints are absolutely everywhere. It's time to check out the evidence. The first clues actually started showing up almost a century ago. Back in 1933, an astronomer named Fritz Zwicky was looking at the Coma cluster of galaxies, and he noticed something really weird. The galaxies were moving so fast, way too fast, that they should have been flinging themselves right out of the cluster. The gravity from all the visible matter just wasn't enough to hold them together. That was the first big hint of some kind of missing mass. But then, in the 1970s, Vera Rubin came along and delivered the real knockout blow with her work on galaxy rotation. And this is the crucial part. Vera Rubin started measuring how fast stars were moving in spiral galaxies. Now, basic physics tells you that the stars on the outer edges should be moving much, much slower than the stars near the dense center. You know, just like how in our solar system, Pluto moves way slower than Mercury. But that is not what she found. The stars on the very edge were zipping along just as fast as the ones in the middle. The only way that makes any sense is if the entire galaxy is sitting inside a huge, invisible halo of matter that's providing all this extra gravity. This right here, this was the smoking gun.
And the evidence just keeps piling up. This is another one of dark matter's fingerprints, something called gravitational lensing. So, you know how Einstein told us that mass literally bends space-time? Well, dark matter has a lot of mass. So as light from a super-distant galaxy travels towards us, its path gets bent and twisted by the gravity of all the invisible dark matter sitting in between. We can actually see these warped and magnified images of galaxies, which lets us map out exactly where the invisible stuff is.
Okay, so with all this overwhelming evidence, the investigation kind of shifted from, does this stuff exist, to, okay, what is it? And for decades, there was a prime suspect that seemed to fit the profile perfectly, a particle they called the WIMP. The WIMP, that stands for Weakly Interacting Massive Particle, it really seemed like the perfect candidate. It was predicted to be heavy, slow-moving, and, this is the key, it would only interact through gravity and the weak nuclear force. And what that means is that it would be totally invisible and it could pass right through normal matter like a ghost. So for years, the entire physics community poured billions of dollars into hunting for this one particle. But here's the big dramatic twist in our investigation. After building these massive, unbelievably sensitive detectors deep underground, and after smashing particles together at nearly the speed of light, we're left with this one nagging question. Where is it? Yeah, the case for the WIMP has gone completely cold. The Large Hadron Collider, it hasn't created any new particles that look anything like a WIMP. Those giant detectors like Lux Zeppelin, which are buried a mile underground to shield them, they've found absolutely nothing. And the telescopes that have been scanning the sky for years looking for the gamma rays you'd expect to see when two WIMPs crash into each other, they've come up empty too. It seems our prime suspect has a rock-solid alibi. So, with the WIMP case basically on ice, detectives have turned their attention to a new and honestly much stranger lead, a candidate that wasn't even dreamed up to solve the dark matter problem in the first place. But it might just be the key. So let's talk about the Axion. This new suspect, well, it couldn't be more different from the old one. While the WIMP was supposed to be this big, heavy, massive particle, the Axion is predicted to be unbelievably lightweight. We're talking potentially trillions of times lighter than a single electron. And that means the way we hunt for them has to be totally different.
Instead of trying to spot a tiny particle collision, experiments are trying to get axions to convert into tiny little flashes of light, photons, by using incredibly powerful magnetic fields. And here's the most fascinating part of the axion's whole story. It wasn't just some random guess that someone cooked up. Physicists actually proposed the axion way back in 1977 to solve a completely separate puzzle, something called the strong CP problem, which basically asks why the strong nuclear force seems to treat matter and antimatter almost exactly the same. The fact that their solution, this theoretical particle called the axion, also just happens to have the perfect properties to be dark matter, well, that's what makes it such an elegant and exciting idea.
But trying to predict how the axion behaves is, well, it's incredibly complicated. These visuals you're seeing are simulations of what the axion field might have looked like in the brand new early universe. See, depending on the exact conditions right after the Big Bang, you could get these tangled messes of cosmic strings and domain walls. How those things evolved determines how many axions are left over today, which makes it a huge challenge to pin down its properties. It's kind of like trying to predict today's weather based on a chaotic storm that happened 13 billion years ago. And this chart here just perfectly illustrates the problem. It shows the predicted mass for the axion, and as you can see, it's not a single number, it's this huge range. And that's because everything depends on when the axion showed up in the early universe. Was it before or after this massive growth spurt called cosmic inflation? Depending on the timing, you get a totally different answer. So we're not just looking for one needle in a haystack, it's more like we're looking for a specific needle across 1,000 different haystacks.
So that brings us to right now. The stakeout is officially on. All across the globe, there are these incredible experiments running, all designed to finally catch a glimpse of this ghost particle, whether it ends up being an axion, a WIMP, or something else we haven't even thought of yet.
The hunt is basically a three-pronged attack. First, you've got direct detection. These huge detectors, usually filled with liquid xenon, just wait impatiently deep underground for a single dark matter particle to bump into one of their atoms. Second is indirect detection. That's where telescopes stare at really dense parts of space, like the center of our galaxy, hoping to spot the byproducts of dark matter like gamma rays. And then there's collider production, basically trying to make the stuff ourselves at places like the Large Hadron Collider.
And these aren't just ideas on a whiteboard. These are real, massive experiments. The Lux-Zeppelin experiment is leading the charge for direct detection. NASA's Fermi telescope is our eye in the sky for those indirect signals. And then you have these really unique experiments like ADMX, which is basically a dark matter radio, carefully tuned to listen for the super faint microwave signal of an axion turning into a photon. The scale of this whole effort is it's monumental.
And yet, even with this incredible global effort, the identity of dark matter is still one of the biggest unsolved mysteries in all of science. We know it's there. We can see the cosmic structures that it's built. We can trace its gravity across billions of light years. But the particle itself, the ghost in the machine, it's still hiding in the shadows.
So that's where our cosmic investigation stands today. The search goes on, pushing the very limits of our technology and our theories. And it leaves all of us with a really profound question. As we keep peering deeper and deeper into the dark, are we on the verge of a breakthrough? Are we about to finally unmask the axion or some other new particle? Or is the universe hiding a secret that's even stranger, something more profound than we can possibly imagine?